All right, let's get started. All right. See, so far, I'm done with the part I'm most confident with, right? So this is a part we cover in this course, and also what's the remaining open problems. I'm pretty confident those are the things. Those open problems are very meaningful, mathematically, scientifically very meaningful problems. The next part will be more speculative, okay? And as I said, the first three types of intelligence are all kind of inductive, has something to do with how we learn a memory, a world model from the world. How do we improve it, right? They have share something common. And we can learn from nature. We can learn from nature. But the next stage, it's a little bit harder because it's a higher level of intelligence. It's very unique to our human. We created it. Right? I call it scientific intelligence. The reason I call it deductive is deductive in nature, mostly deductive in nature， 就是演绎啊。前面是就是归纳啊，早期的这种 intelligence 基本是归纳法啊。那么这是演绎 deductive in nature, and it has a lot to do with science and mathematics, right? So it's kind of the last stage of the intelligence in nature we observe in nature, right? It's unique to human. Right? About 2,000 or 3,000 years ago, we invented a lot of the mathematics, a very abstract notion of it. Right? We'll spell out it. And the information we code are scientific facts, very different from our memory, very different from 对吧? The kind of knowledge we accumulate in history before the invention of science, right? The birth of science and mathematics. Right? And the method is also very different. If you think about it, in the past, it's kind of passive, right? We try and we error. But this one is actually very proactive. We invest, we have, first time we have tools to poke unknowns, right? We can hypothesize using deductive method, either verify and falsify, right? So add piece of knowledge to our library that are tested or proved or verified experimentally, right? So this has very much changed the mode of how to discover knowledge, to create a new knowledge, and even more trustworthy knowledge in a way, right? Again, you can see increasing more frequent efficiency gets improved because now we are doing it actively, proactive, we explore, and also improve the quality of the knowledge. Remember? So you can, it's very interesting, right? History, where something indeed is improving. Not only the efficiency of acquiring knowledge is improving, but also the quality is improving, especially when we have science. Then the question is, what happened? What is behind this phenomenon? What has enabled this level of intelligence? That's what we try to find out, okay? A lot of things are speculative. This has something, actually this has something to do with, a lot to do with the 1956 DATA8014 program, okay? If you read the proposal, right? You try to understand how we form, you try to build a machine to simulate intelligence, but the level of intelligence they talk about is not the level we just talked about this in the previous half lecture is talking about, okay? They talk about how we use language, form abstraction concept, solve problems you reserve for humans. I believe this is not for all humans, okay? This is for educated, enlightened humans, okay? And they improve themselves, right? So hence, now if you compare, right, what we have been doing, right, in the past 10 years, plus years, our, discriminative or generative AI is doing, denoising, compression, object recognition, image generation, text generation, reinforcement learning. This is how we build memory, right? And even a very incomplete one at it, okay? It's very much what behind animal or human as animal is doing, okay? How we build our empirical knowledge, memory, world model is doing, okay? The mechanism-wise, the problem-wise, the methods-wise, okay? Is actually where. And what's really unique to educated, enlightened human is about abstraction. How we come to, how we abstract, create abstraction, logic deduction, causality, hypothesis forming, testing, problem solving, okay? We have barely started this, okay? We're imitating this, but in terms of understanding what this is doing, what is the mechanism allows us to do this, we know very little, almost nothing, okay? We'll talk about it in a minute. Again, right? Just keep in mind, intelligence is not about the regenerating language knowledge already created, right? It is actually about having the ability to create a new language if necessary, a new knowledge. Right? Higher level human, or what we call the deductive intelligence or scientific, is about having the ability to create new abstract concepts. And scientific knowledge will be more specific about it. Right? It's different language, different knowledge, somewhat different. We don't quite know what, but we feel it's different, okay? That's what we're trying to clarify. We're still speculating. Right? So what has caused the emergence of the ability to abstract, right? From, let's say, low-level animal intelligence, the ability to build memory, world model, versus high-level human intelligence, be able to build, right, mathematical abstractions, logic, and deductions, understand those things, right? We do not yet know. If anyone knows, tells me, right? Yes, we know that. Again, guys, this is something very important. Oh, we are taking artificial intelligence course. We teach about the first order logic. Guys, right? Again, logic is the result of the ability to abstract. Okay? It's a product. Just like we're learning, 对吧? 祖传秘方, recipe, right? It's a result of years of mechanism to get there, all right? We're talking about the mechanism. What is the ability allow us to do that, to abstract, not the outcome of it. Of course, once the outcome has given, we can always memorize it, we can always use it. That's a very different process, okay? So hence, we know to build memory, one of the essential process is compression, right? We have learned that in this entire course, right? But abstraction, is this anything different? We don't even quite know what is that process, right? Has something to do with compression, probably, but anything different? Right? Well, then what is the new, if any, objective abstraction? We kind of understand the objective now. Now we know the objective of compression. That's the whole course have taught you that, right? Maximize information gain, get rid of noise, discover the structure, and so on, so blah, blah, blah. But what about abstraction? Again, we feel it's related, but there must be something more, right? Something new. What is it? How abstract then? If we understand the objective, then the question is about how. Just like if the objective is compressed, then we can talk about how to compress, right? Then how is created a form then? Any difference between learned distribution and scientific knowledge, right? As a result, qualitatively, quantitatively, anything different? How we use them differently? We don't know, right? Well, we don't know in general, but we can speculate, right? We can look at some examples, right? We can hopefully understand a little bit. Maybe it's similar or different from compressions, right? Something numbers, equality. See, the notion of equality, right? See, in compression, I have convinced you, right? What is the basic concept behind compression? Group what's similar, separate what's dissimilar. You need a similarity, right? It's enough. 把相似的东西聚在一起，不相似的分开，就这么简单，对不对？ That's what the compression is doing. It's the most basic mechanism, right? But equality somehow, something like equal, it's very precise, right? Has to be something very precise. Just cannot end the word similar. No, that doesn't go with mathematics, right? That has to be equal, right? The numbers and mathematical induction, right? Yes, we do. See, Bayesian is inductive induction, right? 就是经验归纳法. But the mathematical induction is not. It's proof. It generalizes to infinity. 对不对？数学归纳法跟经验的归纳法是完全两回事 right? Well, again, related, 对吧？又是相似，但是又有不同 right? Similar but different. The notion of infinity, from discrete to continuous. How do we build that? Right? Notion of infinity. Right? Again, remember our memory is always based on finite samples, right? We only see finite experience. But how we somehow abstract the notion of infinity, right? Let alone continuous geometric, abstract geometric object, point lines per space, right? And also we start to discover, mathematical deduction, logic, causal relationships. How do we come up and realize all those things, create those knowledge? For example, equal in number, right? When we trade, right? 4个苹果交换4个桃子 right? We have to be able to, our ancestor has to be able to count, right? It's not similar, but its number is the same. Okay? Apple and peaches are different. 4 apples for peaches. But the number has to be the same. They have to be developed the notion of equality. Even discrete one is not that easy. Right? And arithmetics around it. Right? As far as we know, right? And also, even more, the two objects are equal in quality. This is even more. This is continuous quantity. Length, distance, angle, volume has to be the same. Right? We'll talk about, reflection symmetries, and those has something to do with these notions, right? How to go from similarity to absolute equality. Yes, I can draw two triangle. If I stare at it, they look similar. But how in the world I come up with that very absolute equality? Oh, the same angle, same length, right? When do we come to that point to realize? Right? Because similarity works already okay, right? Cats, dogs, they don't have to count. They don't have to know two things are exactly the same. Okay? They don't need this kind of notion. Lossy coding is enough. Right? Right. Well, hence, if we have the prior, past experience, memory, prior, it's good enough. We do Bayesian inferences. Mass majority of the animals survive, mass majority of the humans survive this way, right? We don't need very abstract knowledge, right? This kind of inference is very, very, very powerful. 即是死记硬背, right? Pretty good. Right? Memorize the correlation. Pretty happy, right? We can already survive. We can already do a lot of things, right? Remarkably well, right? Like our entire course is about this. Right, we can do inductive inferences. But the mathematical induction is very different. First of all, it's deterministic, also generalizing indefinitely. Right? We have a prior, if it's true for the base, right? Assuming the prior is true for the k, then also is true for the k plus 1, then it generalizes to everything. Indefinitely for all natural numbers. It's true, right? From finite instances, but the logical relationship allows you to recurse, generalize, just like counting numbers, natural numbers. You stretch that, this recursion, right? Stretch indefinitely. This logic also is rigorous. Right? So it's similar, related to the kind of Bayesian inferences. with a prior, with the induction. But this kind of structure allows you to generalize indefinitely. This is a true generalization, and generalize indefinitely and rigorously, right? And deterministic. It's not even probabilistic. Right? It constitutes as a proof of something absolutely true. And again, see, about 2,000 years ago, people already know this. They developed the notion of numbers, developed the notion of similarities, right? And notion of numbers and the counting system. All Asian civilization come up with the different ways of the counting, right? 十进制还是16进制, right? Mayan counting is 16进制, right? God knows what happened, but anyway, but they count anyway, right? Indian, Chinese, everybody know how to count, right? But the notion of natural numbers, the indefinite number actually only come to about 3,000 years ago. People talk about the mathematics, right? And also, prime numbers are unlimited. Euclid actually proved. Yeah. 数是无穷的. Again, you can probably guess, how do you prove that? Right. So you can always find the next prime numbers, okay? No matter how big it is, right? Come up with a proof of that. Then you can show it. Right. And also, then the people come up with rational, they start to divide, right? It's a fraction, they become more continuous, rational numbers, and continuous infinity, zeros paradox. People struggle in the beginning. They struggle with this, dividing and so on and so forth. But gradually they get it, okay? They formalize it and understand rational numbers, right? 芝诺的 paradox, 大家知道吧？对不对？ You can never cross a bridge because you always reach half, right? So you can never cross a bridge, right? It's kind of like a paradox. But people now, right? And the definition of real numbers, people didn't quite sort it out. They have the notion of the real numbers, but they didn't quite really formalize until pretty late, right? About a few hundred years ago. 建立了实数公理, right? The axioms of they prove actually many different definitions of real numbers are equivalent, right? Again, a notion of complex numbers, right? Or less formalized and so on. Rigorously speaking, we know as a fact, right? All modern large language models do not understand the notion of numbers. It's still true. Basically, by learning, digesting all the text in the world, seeing all the finite instances, no matter how big, the language model cannot learn all the correlations among those symbols. They cannot learn the notion of natural numbers, okay? Rational numbers, let alone real numbers, let alone complex numbers, okay? Forget about it. Let alone the notion of infinity. Yes, it can produce a proof that prime number is infinite, but it has absolutely no understanding what infinity is, okay? Again, geometry, right? Objects, right? People to talk about straight lines. It's kind of odd, right? What is a line? We only see, guys, in reality, we don't only see dots, right? We draw something on the ground, but still, right? So what is the notion of line, right? We start to do abstraction, and also continuously, and stretch. And also when we talk about distance, we start to talk about equality, right? Circle, they realize circle, the radius are equal, and so on. Start to measure distances, and the angles are equal to each other. The notion of equal starts up. Straight lines, linear, right? And also, this one is more important, right? Parallel, 平行公理, right? Parallel postulate, right? Assumption, or whatever you call it, right? Which means that if the two lines are not parallel, they always intersect, okay? But if they are parallel, they never intersect. They stretch for infinity. So it already has the notion of infinity in it, right? How did we know? See, now this is a question. We already know, right? The delta R is the compression to linearize, right? But that's what the process is. Actually, the compression never know what is the end. You just try to make things simple, but they never know actually it has reached the line beneath it, the subspace behind it. how do we realize the importance of we're linearizing something, we're making something simple. Suddenly we know the limit is actually which a line, which a plane, which a subspace has a notion of linearity, the linear objects. We don't know, right? And how do we go to finite to infinite? Where that emerge, this notion of infinity emerge, right? What is in our brain trigger that? Does animal has similar mechanism, but just has not been triggered? I don't know. We don't know. Okay. How is this related to the compression? Right, making things simple. We actually don't know. But we do know, right? I mean, see, inductive in our memory, so far we are all doing inductive inferences based on correlation. Basically, we capture the distribution. 对吧? But the logic study principle deduction that ensure correctness of inference or reasoning, right? For example, people have an informal logic. This is about the language. Formal logic, since Aristotle, there's the 三段论, 对不对? Start with classical, propositional, and the first order, and so on and so forth. It's different variants. And also then there's a formal mathematical logic. Gets formalized in 19th century. Russell, Cantor, Hilbert, Gödel. And also computational logic, Boolean, Turing, Shannon, and so on. Right? So try to implement logic. Causality, causal inference, is try to study the necessary effect of some event on the change of others, right? 康德啊，这个还有这个 Pearl 的 some more formal， right? 这是图灵奖得主 ，right? Julia Pearl, right? Now, big question is, right? See, one thing at least to stand out, this kind of inferences are kind of probabilistic, right? But those are both kind of deterministic, right? At least correlation. And can logic and causality be learned from data distributions? Can you learn causality or logic from you see enough instances? From data distribution? Actually, the answer is quite no, right? See, generally speaking, correlation are X and Y are correlated through we describe them as a distribution, right? We talk about this whole semester, right? How do we, X and Y are correlated, we can learn P of X, right? Or expressed as if it's low dimensional, we can represent it as fx, y equals 0, right? Write down as equation, right? Add some constraints to it. Logic is actually talk about the sufficiency. X implies Y. If some X is true, enough statements is true, that implies Y is true. Okay? It's actually capturing the sufficient to be rigorous for your argument. Okay? Causality is a little bit opposite. It's capture some necessity. X is necessary for X to something else to change. 对不对？比如打伞，下雨了。Something triggered. Something caused something else to change. Okay? The causality is a causal effect. Hence, causal effect in nature always reveals through time dependency. X the change in X, which is derivative, right, of X, depends on some input U. U cause X to change. Okay, so that's why you realize, right, why we write a lot of laws are in terms of derivatives. 微积分就有帮助了，对不对？ Or implicitly, right? Almost all physical laws are written this way. Okay, no exception. Always capture what is causing what is affecting what. Okay? Unfortunately, actually, but the distribution capture only correlation, but not the logical causal relationship. In fact, for example, if X representing raining, Y representing umbrella, you can always learn that, right? You see that whenever you see raining, there's an umbrella. Whenever you see umbrella, there's raining, right? So the machine will tend to believe whenever I open if you see umbrella, there must be raining, okay? which one is causing what? Necessarily. That's why many of the video generation, right? You can see, if some people open up the umbrella, then start to raining, all right, so on and so forth. It's not water raining and it causes water. So this is actually a lot of things. Turns out, actually, if you read the causality, the book that Julia Pearl says, in fact, causal relationship is precisely mathematically, it's precisely a relationship you cannot learn from the distribution, from correlation. 明白吗？正好是你从 correlation 从 distribution 里面学不到的东西，才决定谁在影响学。是 beyond how x and y are correlated. You have to solve on top of that. You know they're correlated, but on top of that, you have to do something extra to identify if x is causing y or y is causing x, or they don't have no effect on each other. Okay, you have to do something extra. It's called counterfactual experimentation. It has something to do with science. You have to make a hypothesis, deduce, verify, design algorithm to falsify or verify whether or not x is causing y or y is causing x. Okay, that's right. Anyway, we're just doing this very sketchily. I just tells you that distribution can only capture only correlation, but not logical causal relationships. Okay. Right. Hence, a key question. Right. Well, you can see there's something, right? I mean, in terms of knowledge, even in terms of knowledge, I'm not talking about the mechanism. I just talk about the knowledge, right? So, see, if I have the ability just to remember the distribution, I see enough instances of those samples from those physical laws, right? I can representing them. I can learn the structure from the data. Just like an animal, right? Animals, see, cats still knows gravity, how gravity works. Dogs too, right? They learn how to, they have a world model, but they describe it in the neural networks, like the low dimensional distribution among data, right? Here, of course, we have those physical laws, right? Describe how things work. Is there any difference? For human, I just remember I have my physical world model by observing how a ball bounces versus understanding those equations. Is there a difference? When I try to apply it, what's the difference? 这有没有区别？大家去想一想。有一点像啊，就我刷很多题，对不对？ I see many instances. I probably still can get a very good score in testing. I see the relationships among things. Versus, I actually truly understand the deductive, the logic, right? The mathematical theory, right? I truly understand it and apply it correctly. 我是刷了5000题，对吧？几米多围棋5000题 ，right? I can do pretty well, right? With calculus, pretty sure. Right? Even I may not necessarily actually understand what the heck I'm doing, or even the durations, right? I don't have to, but I memorize all the pattern, right? So is there a difference between even memorizing something and understanding those laws, mathematical abstraction? So the question is, what they actually give us extra, basically? Even as knowledge, 明白吗？还别说我们 discover 的 method 不一样啊，先不谈了啊。Compression 跟 abstraction, if there is any difference between compression and abstraction? But how do we But even after results, is the output, even the outcome, even the results of these two processes, are there any difference? Somehow they describe the same thing, right? At least for the physical phenomena, right? This is written in manifolds. This is written in another language, right? In different, are there any differences? I don't know, right? But one thing, right? So somehow Richard Feynman says a little bit, something catch my eyes, right? So if we cannot self-create it, So somehow we don't understand. So the understanding has something how I have to recreate this knowledge, go through this abstraction myself. Hence I can understand. 明白吗？所以我们在训练不是通过刷题 ，somehow we have to recreate the theory almost, right? From almost first principle, from the assumptions to do the deduction ourselves, to see how logic works, to see how every steps works, right? To recreate things in our brain, be able to understand what the heck those things mean, rather than just memorize them intuitively, inductively. So even the two forms of knowledge, even those two knowledges, our memory and knowledge, are describing the same physical phenomena. Somehow there is a difference. Abstract knowledge versus empirical knowledge, still there's differences, okay? And what is it? What do we get to learn? What do we get to gain extra if we understand those phenomena in terms of this kind of physical, in terms of those abstractions? Think about it， 哎，对吧？从实用的功能上 ，from the pragmatic purpose, right, almost the same. 用来 predict 嘛， right? If I capture or if I have enough data, right, somehow I seem to know all the equations in the world, right? It's kind of equivalent, quote unquote, but still something is missing. By abstraction, get it out, not get it out, right? See, I still have this process of compression. I still can compress, right? This organize those instances into a line, but realizing there is a line underneath somehow give me something interesting, extra. You know what I mean? Be able to write down that equations, rather than just having that denoising process to accessing that structure. Somehow, the abstraction. Let's say something. What do we get out of the abstraction, right? So as I said, remember, I keep asking this question, right? What is the objective of abstraction? 知道吧? What do we get out of it? Beyond this kind of inductive compression process. The process also discovers structures, right? Maybe not the causal, maybe not logical, but at least most of it. Maybe physical laws capture the causality. Maybe that's the case. Okay? Maybe those abstractions allow us to capture causality better, capture logic dependency better. Maybe that's it. But what is actual takes to us to get it, to realize, to produce those abstractions? I don't know. Right. Go beyond the correlation and discover causality. Think about it. Hence, you can see, right? Right? I mean, so we say from alchemy to science, right? 炼金术啊，到科学, right? The method, right? Even since that, if you think about the method, they're also it's kind of similar, but this is also some fundamental distance. For example, for nature, empirical alchemy is always try and error, right? 试一试嘛, right? Try different things. It's just like different recipes. We try this and try that. Even even for Newton, right? I mean, Newton is very good at the physics, but he's very bad at chemistry, right? Even that when he's old, he's still trying to make gold out of 炼金，对吧？他还在做炼金术 he's trying to make gold out of the 铅吧，是吗？ Anyway, right? Good luck, right? But he's trying, right? Hypothesize, right? So the science is very different, right? They hypothesize, then falsify, verify, falsify, 对吧? Conduct an experiment. And prove a contradiction. Mathematics is also mathematics is just the axiom system. We make sure it's self-consistent, right? There's no contradiction. Science is there's no make sure your hypothesis is consistent with your experiment. Doesn't cause. So you can see that the science and mathematics is actually using very, very similar procedures, right? You make a conjecture or hypothesis, then you conduct a logic deduction, right? To derive all implied conclusions, implications, until you reach a contradiction. or inconsistent with your experiment, then you falsify or reject your conjecture, right? This is almost a normal practice in math. But this relies on what? This relies on fully understand logic, the deductive methodology, right? Understand what is sufficient, what is necessary for things to be true, to be false. Okay? The notion of logic and causality and go beyond just correlation, right? It's a very deterministic. And you can see that's why, right? And very different from mathematics. You know the difference between mathematics and the science, right? Mathematics is self-consistent. Any mathematical system only has to be self-consistent as long as the assumptions do not contains contradiction. You can play. You can derive whatever the assumption implies. Although Gödel says there may be some true statement you can never derive, prove, but that doesn't affect the self-consistency. Right? You can still keep going, prove what can be proved. Okay, but science is different. Science is always try to develop a theory that is maximally consistent to the nature, to the environment, to the physics of the world, right? In some things, all scientific theory are falsifiable. Those things, unless you are God, right? Unless you believe there's a God. All scientific theories are falsifiable, right? This is Karl Popper. So we're always, so that's why in the science is always 在路上, always on the road to improve, okay? To modify, to correct. Hence, scientific activity are precisely the embodiment of intelligence to self-correct. Always, always self-correct, okay? So now the question is, now we talk about it, then how do we know from engineering side, right? From now, remember, we try to understand the mechanism of how we form memory, intelligence, is not just to understand it, right? As a scientist or as a mathematician, we are computer scientists. We wanted to not once we understand the science and mathematics of intelligence, we also want to know, once we understand the mechanism behind it, we want to implement it. We want to re-implement it, right? With some physical mechanisms, right? 碳基硅基 carbon-based or whatever, silicon-based or photon-based, quantum-based, whatever efficient, right? We try to implement it. Now, the question is, how do we know we have done a good job? If a system claims they have achieved certain level of intelligence, how in the world do we know? How do we test? Right? 那你看现在为什么大家在刷分，对吧？ There's a lot of benchmarks out there, right? 三天两头, once a while, there's a few percent better, right? Although everybody is doing the same darn thing, right? Google 又说我又睡，对吧？一会儿 there's always another 地表最强的 AI come out, right? And another 15 minutes of fame, and always. I mean, it's just a silly game. But the question is, it's okay for industry to do that, for engineering to do that. But the point is that it's like a sports, right? Think about it right now. It's going on with all the big models. It's like a sport. Think about it. Just think about you are watching an NFL football, right? Or a race, 100-meter race. There's always someone gets better, break the world record. That's it. It's become entertainment. Okay, that's kind of what it is. Okay, you pay $1 billion to play a game, but no, for us scientists, researchers, we have to be very serious, right? We want to understand things once for all. How can we test? Because now their industry is saying, oh, the system already have intelligence, or even the system already have conscious. Right? The system can already self-learn. Really? Those are all claims. Those are all opinions. They are not conclusions. They're not scientific conclusions, guys. Now, it's our job to decide. how to develop rigorous tests that can scientifically certify different levels of intelligence or stuff. Or if it cannot be certified in a theoretical or rigorous way, just tell us. Why study whether they can be certified at all? Right? Whether there is a difference between P equal to NP. If, just like the problem that Turing faces, what is computable, what is not computable? OK? 一样的问题，对吧？能不能分开？分不开吗？ Can we separate them? Right? What is P? What is NP? Can we separate them? Is there a separation? Study it. Make this a scientific or mathematical problem. 明白吗? Understood? Right. Now, for example, if someone say the system can self-learn, truly, really, whether developing memory via reinforcement or supervision, or the system truly autonomously learn memory, create the memory themselves, so it actually understand what it had learned, just like Feynman has said, 对不对? Or it's just end-to-end some OpenAI engineers supervise or select models, select data, supervise, learn. Claim the system is self-conscious, right? No. Or self-learn. No, it doesn't. Okay? The second, Turing test, whether it's only memory-based inductive inferences or truly understand law or rule-based deductive inferences. Just like a human, educated human, we understand something. We're solving the problem as a mathematician, solving mathematical as a mathematician that understand the subject. Versus a machine have seen a lot of examples of the subject, be able to memorize the solutions. Okay, how can you separate that? I think this is what Turing has in mind. Really, the machine is doing something only unique for human can do. Okay, if we believe abstraction and compression are different, okay, understanding abstract knowledge and empirical knowledge are different. Okay, if third, right? Whether there's also people claim, oh, large language model is really can do research now, right? Can replace PhDs, right? Can, do science. Really? Right? Can it really, whether it's really developing empirical knowledge, well, compression, or actually be able to create mathematical new math, if there is any new thing, really have the ability to create something abstract that has certain value. Again, remember, we don't know what the value of abstraction is yet. But if there is value, right, then the machine should be able to, based on that value, to do something better, right? If there's new vocabulary, there's new entity, we have never even named it. The super intelligence should be able to realize, oh, you guys should name this one, okay? 一个新品种的水果, right? Give a name. Has that ability to abstract, create a name, create language, identify relationships, even hypothesize the theory to explain the phenomena, right? Really conduct the kind of activity as a scientist, right? Then start with the hypothesis, do deduction rigorously, and be able to conduct experiment, verify, falsify, so on. Do all the things, right? Truly understand what it's doing, not just emulating, right? Right. You can see, right? So even Karl Popper says, I mean, yes, there are collections. Compression, abstraction, maybe there are connections, but maybe it's a limit. There's something qualitative different. 我们说量变引起质变，对不对? There's a jump in the behavior, right? From gradually at some point we are able to, right? Science may be described as the art of systematic oversimplification. Right? Through the process of compression, we suddenly realize certain abstract notion, it's more generalizable, and so on, become deterministic. The relationship from probabilistic become deterministic, right? And so on and so forth. From correlation become causal, become logical, so on and so forth, right? And there's some extra value attached to it. Maybe generalizability, or, right? How do we test, right? I mean, this is just a proposal, right? So can we really test something is just reinforced, learned, or self-learned, right? I call it a Wiener test. And also another one is, is really inductive, just machine, just memory, or it's actually deductive, understand, based on understanding. Understand abstract knowledge, abstract rules, right? Be able to just like human, educated human, And also, of course, just compress, do things empirically, like we have been doing thousands of years. Animal can do it, compress, organize, build organized memory, versus abstract. Through the linearization, realize, oh, that's linear, write the equation. Okay. Now it's not that easy, right? The question is, we already passed Turing test, right? All the machine we got even better than humans, get the scores, get better scores than human. Really? Are those really scientifically sound conclusions, right? Then why they still don't have the notion of numbers, so right? So then the question then to have a test to be scientific, we really have to be very, very serious, right? Or who are qualified to conduct such test? OpenAI, Google, a bunch of engineers, or some so-called self-labeled experts? We don't know. Is a community? Even a community making all kinds of stupid mistakes, okay? It's not trustworthy, okay? What is the factual process? What are scientific sound procedures, question, or task to test? Right? Not by some authority, okay? No, it cannot. Science, there's no authority, but it has to be scientifically verifiable process. And how to draw meaningful. Then, if those can be defined, okay, then is from the results. How many score? Based on the results, how do you draw meaningful conclusions? Pass, non pass? What is the criteria? Okay, it's not that kind of easy. 60分及格那是很 arbitrary, 对不对？70分 I don't know, right? Do you even score them? I don't know, right? It's a binary, right? So those are actually pretty deep and interesting questions, right? I think that this time, right, it's really important for scientific community, mathematics community, or machine intelligence community to be very, very serious now. Okay, those are very good problems. We have to study them, have to address those, right? At least compare the existing benchmark system, how they're doing, how scientific they are. Right? We don't know how to do it, to be honest, guys. I think nobody has a clue. Right? I mean, there's some effort, right? Just give it a little bit of effort, right? Still, people are interested. This is a bunch of folks at try to understand, right? For example, there's a lot of says big models are get Olympic gold models, gold medals, and so on and so forth, right? At least they may be useful. Even Tao Zhixian claimed that he used large language models. But again, of course, even any book in the library can be very useful for me to solve a 100 years old problem. Okay? Remember? Maybe search, if I'm lucky, if I send the right query on the Google search, I might find something relevant to help me. 明白吗，同学们？ Don't ever overstate. Find what the truth is, right? So the question is that there's some effort. I mean, even there is no such program. I mean, some people, including I, got involved a little bit. Those are just a bunch of mostly the mathematics PhDs from different universities from Caltech, Berkeley, Stanford, and so on. Those guys are actually majority of them are actually Olympia gold medalists. They're young PhD students, math students. They're actually curious about what the mathematics is doing. Right? They want to test more. I think Tianze is also recently later involved in this. And how do we evaluate, right? Such as any system at all? If you come out, right? What is the really skills, right? 在一个数学题上 got a very good score, passing score on some tough, so-called tough questions. By the way, guys, if you have $10 billion, right, you can prepare data very similar to any benchmarks, okay? Even you don't quote unquote cheat, training on the same data sets, okay? But once you know what the test is, you can produce data very similar to the nature of the test. 明白吗，同学们？ 不要那么容易相信啊，这个 test 好吧，对吧？这个世界没那么公平啊，有 resource 跟没 resource，有 someone rich。Oh, you say, oh, they're doing blind test, right? Must be very trustworthy. Are you kidding me? 你们不会这么 shallow 吧，同学们？Blind test is trustworthy? They don't know what the questions are, right? 那你这还天真，你们做学问还没有入门呢，对不对？做科学，如果这么去想的话，OK？Why? There is something called reinforcement learning, right? If you have access to the test set, you can always what? Tweak based on the score. OK? 明白吗？ So that's why, a fair blind test is limit number of access. Once there's not you cannot even do multiple access. You can only access one. He access one. He access one. If 5 people access it, throw it away, redo everything. Even this cannot truly guarantee against someone extremely resourceful. 明白吗？对吧？所以要知道，要很 resource is a determining factor. If you have a limited test, it's a very important concept. Okay, be a little bit rigorous about your deduction, right? 对吧？所以你看，包括很多那个，你知道制药对不对 ？Drugs test, they do blind testing, but that's exactly the protocol, right? Once you get the test they pass, implies billions of dollars. Okay, that's a very so hence if you allow the pharmaceutical company to access the test set indefinitely, they can easily throw billions of dollars, easily pass that, right? Overfitted data sets, even they don't know what it is. Okay, that's called a reinforced learning. You can just these are a lot of resources to just constantly try, see tweak which one can get a better score. Okay. It's very, very easy. Let alone, right, a lot of those tests these days are not that blind, okay? They're actually at least gray, okay? They're not black box, they're actually a gray box. I mean, you actually know what kind of question, at least similar question there. And you can actually prepare the logic. There's a lot of things you can do, right? So the question, how do you reach very rigorous testing is still open question, I think, right? For example, big question. Can you come up with a test that say any system can definitely solve, create, understand the notion of numbers? I don't know. Who's the one? Tenza, who said that they can do the largest model right now? What is the number of digits they can multiply or do arithmetics? Few hundred? Yeah. I think 那天开会是谁说的some students tested a lot of big model can do a few hundred digits arithmetics, but go beyond that, everything is messed up. Okay, 因为现在 token 不是越来越长嘛 ，right? The longer token, now they can do more and more multiplications, but you can train, right? You can train a lot of correlations, but still they don't even master the arithmetics. 就加减乘除还是不会的。So this is actually very interesting, right? Of course, you can say, well, every time I can have a big language model to query a calculator, right? We call that cheating, right? You don't learn. You actually ask an expert to do that for you. Again, that knowledge of calculator is encoded. Calculator doesn't understand arithmetics. Just follow the rules, okay? So guys, be very, very careful. How do you test the system's capability is a very, very tricky thing, okay? It's not necessarily the result tells what it is. Hence, there's a lot of things in the literature or in the community, in the industry, is very misleading about the notion of intelligence, the capability of intelligence, how they test it, how they claim they tested it, and so on and so forth. So, but hence, this is exactly, I think, academia needs to do more, right? This is exactly the responsibility of the community, academic community, you guys, researchers, to clarify. There are truly, time for heroes. Okay? Just like Turing, right? Tell us what is computable and what is not computable. Sharon told us how information is measured. Before that, it's very vague. People don't know what to do. OK， 这就是这个时代就是最重要的时候，对不对？就是在大家都不知道该做什么时候，你告诉大家该做什么，什么是正确的 ，What is the right thing to do? OK， those are why those people are memorized for the rest of the history， 对吧 ？They precisely tell us to clarify things before them. People don't know how to clarify. Right. For example, even Wiener, he a long time he realized the importance of information, but he doesn't know how to measure it. But he knows it's a concept, it's important. It's kind of vague, kind of intuitive. Until his, Shannon actually did a very good job, right? Clarified how to measure information and so on and so forth. So the same with Popper, right? About the science, what science is doing, right? Why he's famous? Because a lot of times we don't understand what science is doing, the nature of science and so on, right? So be able to clarify, right? How do we truly be able to measure, really reach meaningful, scientifically sound conclusions based on what test? Or are those things even testable at all, certifiable at all? We don't know, okay? But be able to clarify the questions is something important. Even this one, the evaluation is still, again, kind of empirical, right? They look at, the produce new problem solutions, probably unlikely has been seen by some of the large language models. And also they look very carefully with the procedure of solving, rather than whether or not it's right or wrong, but they look at how the machine actually, maybe how they conduct the inferences, deduction, and so on. Which part they make mistakes or which part they don't, and so on. Right? Try to do more detailed analysis about this, but it's a lot of effort, right? Even this protocol may not be, right? I think Tensor probably know more, right? Maybe all the big companies also doing similar things. But their purpose is probably try to identify the problems so maybe they can improve it, right? Maybe train on some more new data, see which type of problems, which type of skills are still weak, so maybe do some remedy. But here, of course, I think ultimately academia, we want to find out, right? Not just to say that, not just to find out the problem, say we can just find a patched on solution, 对吧? Band-aid-like solution. They are very bad with this type of questions. Maybe let's build more training data. Yeah. 不是这种啊. Try to identify what's fundamentally missing. Right? Things cannot be fixed by just adding more data or more instances. Right? To add some fundamentally new mechanism so the system will behave very, very differently. Right? To reach, remember that jump from empirical knowledge to abstraction, to realize, right? Remember Richard Feynman said, right? Somehow the machine system has to be somehow recreate that abstraction process. Hence be truly understand those abstract knowledge, understand its purpose, right? To reach that point, rather than just receive it, learn, and regenerate it. That's not probably reach the notion of understanding. Right? All right, that's very much for this lecture. We'll have a couple of minutes to just say if you guys have any questions regarding to this lecture, right? I just want to summarize the book, the course, tell you a little bit about maybe a little bit of the concept, principle behind inductive intelligence. And the second half of the lecture is mostly speculative, but I think it has quite a few very valuable questions, right? Hopefully those questions allows you to clarify a lot of things, right? Many of you have still very young, have a long career. I believe that some of you will probably embark on some of those questions, right? Looking forward in the future, right? At least some of those questions, we may have some answers or some good proposal. How do we approach them? And how do we really approach the mechanism behind how do we develop deductive intelligence, right? Ability to create abstract knowledge, such as mathematics and science. All right, that's all. Any other questions? Still have a few minutes. As I said, the time is to speculate, right? I wish in the winter, right？你们可以好好想一想，下一步自己做点什么。现在有很多非常有意义的问题，而不是一些现在If you just want to learn something to find a job, so be it. But be careful, right? Those jobs may not last. Okay. Right. And I'm pretty sure, right? A lot of people are be able to do the same thing very quickly. Right? So, and in terms of research, right, you can see just that's why there are 10,000 papers every year, right? Because all the papers are the same. Even high school kids can do very much the same thing. So what separates you from those? Right? And there's plenty of problems. Plenty of the landscape allows you to go much further, much better. Right? So, yeah, my advice is that don't think that all the big companies say, oh, this is the only way. Okay, no, it's not. It's far from the only way. They probably have gone a little bit further in one way, right? But definitely they're not going to reach the goals, right? As far as we understand, the kind of goals that the world's pursuing, right? Yeah. So you guys have a lot of opportunities there. 有没有什么问题没有？那最后有机会。Question. Well, I mean, maybe as I said, right? Yes, I think that right now we kind of working on one types of representations. As we already know, right? Even the abstraction, mathematical abstraction is already capturing more discrete type of. For spatial representation, maybe you want to, some kind of cells. I don't know. Some kind of other structural representations, right? Discrete types or structured ones, group invariants and so on, right? It's far beyond just a linear system, linear subspaces. Those are the most basic one, but definitely not capture some more refined structure in the data, and let alone logic dependency, causal dependency, right? So, all the causal inference, people actually using graphical directed graphs to represent it. I don't know. I'm not saying that's the optimal one, that's the best one, but those relationships do deserve a class of representation beyond what we have studied in this course, right? The kind of capturing just the subspace, the statistical behavior structure of the data. Yeah. But how we go beyond that, even how we actually abstract the knowledge, the language. Language is not a modality. Language is the code we learn. Okay. Language is a representation. Natural language is a representation. And mathematics is another representation. They represent different typologies. Right? So it depends on really what the structure of the logic represents. You definitely will converge on different type of internal structural representations, for sure. But again, one common problem is that what that representation is trying to optimize. What is the purpose of that? Right? Why we develop the mathematical language? Why it's not enough? Right? Why we have to abstract? Why linearization not enough? Have to realize what the limit is. Why just equipped with the ability to linearize is not enough. Actually be able to realize this, create a notion behind this is good, line is good, plane is good, linear system is good, linear subject is good, right? This is our goal, to reach this kind of abstract understanding. So history, in a sense, mathematics is already very different than representation for knowledges beyond the empirical representation that we learn in this class. So yeah. And honestly, for language, don't think about language. You need a representation. Language is just a symbol, right? 你可以说中文是英文的另一种 representation， 对吧？俄语是英文的第二种 representation. You can represent. We already have thousands of different representation of languages. We're all doing the same thing, the different code book. 明白吗？啊。I don't think of Frankenstein is good. I don't think he's good. He's right about everything. His understanding is pretty limited. Right? Right. So guys, you guys, even my age, I can tell you, we're too young to be philosophical. Okay, when you retire, it's time to be philosophical. That's my best advice to you guys. Right? Stay away from philosophical thinking, because that's not going to get you anywhere. Right? Because there's way too enough exciting scientific mathematical question left for us to study. Okay? Only when you have exhausted them, that's the time to be philosophical. Okay? Even today, right? You can see the second half of class, I can afford. That's after 10 years of my study. Okay? We kind of understand a little bit about the memory. Now, maybe I can have a little bit of freedom to speculate a little bit. But even when I'm speculating, I try myself the hardest. Stay with being philosophical. Remember, don't take philosophical conclusions or projections to guide your future quest for scientific mathematical problems. Don't ever do that. Right? Philosophers, they have a different purpose in life. Okay? Their advice, their conclusion are far from what we are trying to do. Right? They have their values, right? But it's definitely different from what, right? The few person you want to read, maybe if you have time, Popper or some scientific philosophers, right? Even then, don't take everything. Okay? Most important thing when you do research, be critical. Stay being very, very critical, including what I taught in the class. Okay? Don't trust anyone or conclusion until you have built the chain of evidence yourself, either theoretical or experimental. Right? Don't rush to accept conclusions. Right? Remember this sentence. If you cannot recreate that process of thinking, you don't understand. Hence, you don't take that conclusions. Right? Build your own chain of thought, chain of conclusions, right? To then draw conclusions. Especially don't take philosophical conclusions, right? To give you excuse not to do certain things. There's fast of things, right? Even this lecture, I already told you there's plenty of already very scientifically or mathematically sound problems. Probably already, exhaust most of your life. Okay? For you to find answers to, right? Even second half of the lecture, right? About the next level abstraction. Again, it's a fact. It's a phenomenon. There's nothing too philosophical about it. Right? It's a phenomenon already taken place. There's an existing solution. Find it out. What is a scientific mathematical explanation to it? Right? Just like physics. Intelligence is a phenomenon. As I said in the very first lecture, right? Physics studies the law of the universe. Intelligence is studying the laws of life. Both are physical phenomena. They are not hypothetical. They are not philosophical, right? That's intelligence. we don't want to get into sentiment or other things, right? Sentient consciousness, let's not do that yet, right? 就是这什么这个情感或者是什么理智，我们先不要去管那些东西，对吧？但是 the function of intelligence systems, right? How do we learn knowledge, build memory? How do we use them for our daily life, for prediction? And those, I believe, can be studied purely as scientific mathematical problems. Okay? Anything beyond that? For now, try to stay a little bit away. 喝醉之后可以想一想. All right, once you get drunk, you can think about it or argue with them. But don't mix that with your true mission. Okay, and try to. There's a great questions, right? Scientific, mathematical questions. You really should be focused on, right? Because this is the one you actually have a chance to carve out and claim the territory, right? As part of news, right? As I said. Right? Understanding the mechanism behind intelligence is probably really requires the convergence of science and mathematics and computing together. And this is very exciting. And we think we kind of see a little bit of light how to do that, right? The second part, the abstract part, I don't know, but it's related. Definitely those two see, later doesn't do completely reinvent anything completely, right? Even the first three stages of intelligence are quite related. They're progressive. Only there's a jump. There's another jump, right? 量变引起质变, right? There's another jump. Right? There is some critical, 对吧？叫基点效应啊，或者 whatever you call it, right? But it's progressive. It's improving the efficiency, quality of knowledge. Right? It might be related, but how? Precisely how? We don't know. Maybe abstraction is extreme form of simplification, compression, maybe, but then build that theory, right? Make it rigorous. What is X-ray trying to do? What is the quantity? It's trying to optimize. Okay, what do we gain from it? Why we do that, 对吧？只知其然，实际上我们现在都是对 intelligence， 我们只是真的是知其然，只是看到现象，但我们不知其所以然，明白吗 ？Why? Right? What is the purpose behind it? What is driving it? Right? This is actually, I think, it's a very, very exciting time. I think for most of you, right? 所以有时候不要去 focus on 很多东西，对吧？这是做 research. If you want a career in research, right? This is probably the most exciting time, but not because there's a lot of people are investing billions of dollars on something we already know, right? 就跟我们已经知道好如何去砌墙，对不对？不管是 build 一个 house 也好，还是 build 一个长城 ，right? It's up to how much resource you have, right? How much reward you get from it. That's a complete business decision, right? Engineering decision. Has nothing to do with the science, right? So the unknowns, right? There's plenty of unknowns here. Even this part, right? Even this part, how to do it correctly, how to do it most efficiently. I mean, even at the animal part, we have a long way to go, right? Let alone this part. We really have little knowledge about it, or at least understanding about it, right? So this is interesting. One more question, last one, 5 minutes. Even about our project. 所以避免做一些，现在我就是刚才不要，就是说学去把现在你做的东西学懂是可以的，但不要 research 要避免去做很同质化的东西啊。这是就是 be very critical， 一定要非常 one thing right。所以我不是说嘛，I always emphasize right. I mean, 3 C's right. First, be curious. You have to be curious. Okay, guys. If you're not even curious about the second is be critical. Just curious is not enough. 好奇对 intelligence 好奇不了 has to be critical. What people really understand, right? People say all kinds of crazy things, right? Do you have the ability to verify, to criticize, right? To ask their motives, ask their evidences, ask for their reasons, okay? If those reasons are not convincing, don't believe it. Then the last thing is creative. Then find your own answers. Find your own approaches. You see, in this course, if anything you forgot about course, the knowledge we taught in this course may not be that important. But you see, through this course, you have seen a lot of history, right? How things were built, how better understanding was achieved, right? And very often, what we see is that 有时候真理往往掌握在少数人手上啊 right? The whole community, the whole scientific community may be embarking on something very, very weird, right? They believe something else, right? A few people really, 对吧？经常有那么几个人站出来说那也未必，对不对？啊，这几个人还真的 But every field I've seen that, right? Early information theory, control theory, right? Signal processing, right? High dimensional geometry, optimization, right? All the field, including even deep networks, right? There's always, you can see very often, repeatedly, again, that's how truly, that's actually the characteristic of intelligence. Because you always try to correct the existing know-how. 知道吗？所以一个 scientific community 真正的最本质的特征就是要纠正、改进现有的知识、现有的体系，这是它最大的 value。If a system already just repeating to believe we already know everything， 对吧？我们已经知道所有东西了，无非就是小改改，对吧？实现好，实现越大越好，越多越好就完了。那我们也就 then we are become non-intelligent， 对吧？ We don't have intelligence anymore， 对吧？ We become a copy machine, right? So this is something very basic, okay, guys? Remember those, right? There's and if you want to do something new, this is a great landscape. Because unlike physics, understanding intelligence is probably even more important than understanding physics, okay? But yet, mechanism of intelligence is a severely understudied subject, unlike 100 years of history about physics, right? Try to understand, try to understand, know a little bit of intelligence just only 80 years ago, right? But seriously, truly to try to understand scientific and the mathematical problem behind intelligence, I think it's just past a few years. We become very, very serious about it, right? Remember, this is your chance, right? Right. And this is about understanding, if not all life, at least a very big part of life, right? 生命是在干什么啊？ This is a very big part of it. Maybe not all, but at least a big part of it, right? 所以现在这些问题很有趣啊，所以现在我觉得是很好的时间啊。I hope everybody will prepare yourself, and hopefully this course gave you a little bit of introduction to this truly wonderful field, right? And for reasons, probably most people, mass majority of people in the world have not realized it. Okay, now you are the first batch, so take some advantage of it, right? All right, so you have 2 weeks for your final project. I really looking forward to see something a little bit out of our box. Try to be a little bit self-critical, right? Even you fail dramatically, okay? Right? And try some crazy ideas, right? And it's time to be crazy a little bit, right? And the last thing you want to be is more of the same, okay? I mean, it will be very disappointing. Okay, good. Do that on your part-time, right? Don't do it, as your serious research, right? All right, good. Hope everybody have a wonderful final weeks. All right, see you guys.